Yeah, in this video, we are going to talk about wooden beam design. How can we design this wooden beam? So look at here, and we can find out the provided data here. The first one is clear span, and the clear span is 5 meter, whereas the support wall thickness is 230 mm, and load on the beam is 20 kN per meter. Also, there is some properties of that wood, and that these are permissible stress in bending tension, that is 16 newton per mm square, and bending compression, that is 16 newton per mm square, as the material is homogeneous, uh, and its permissible stress in bending tension and bending compression is same. Okay, that's why these values are same. So we have also permissible stress in shear, that is 30 newton per mm square, and permissible stress in compression perpendicular to the grain, that is 3.5 newton per mm square. And the last one property of the wood, that is modulus of elasticity, E, that is equal to 1.2 multiplied by 10 to the power 20 per m square. So okay, the question is like this. Here is the beam. So a beam is simply supported here and like this, and we have the value, the clear span is, okay, clear span of the beam. This it is better to uh, make a diagram in this way. Just it is just a like a symbolic representation of that system. But before doing this one, I would like to, okay, make this one diagram. So look at here, this is the column, or you can say this is the support wall. We there is the value of, or the dimension of the support wall, which is 230 mm, and this is the support wall thickness 230 mm, and this is the beam over the support wall, like here, like this one. Okay, so this is the beam. Okay, this like this, and the applied load on here is UDL, and the value of that load is 20 kN per meter. Okay, so the clear span is 5 meter, and the support wall thickness is 230 mm. 230 mm. Okay, and then the modulus loss of elasticity, that is E equal to 1.2 times 10 to the power 4 Newton per mm square. As I said earlier in the previous video, we are doing all the calculation in Newton and mm. So we need to convert that value into Newton mm. If the unit in, for example, bending compression, bending tension, or even modulus of elasticity, you should just convert this value into Newton mm unit. Okay, so so go here. So first of all, just you have to calculate the value of effective length, yeah, that which is denoted by YALI. So the how can you calculate the value of LE, that is effective length of the system? So we can calculate by using this equation, or just look at the figure. You can understand how it is calculated. So the effective length is kilospan is plus support with half of the support width from this side and half of the support width from this side. So altogether, the total value of effective length is 5230 mm. Okay, you can calculate the effective length in this way. This is actually, this is the this is in the case of simply supported system, we can use this way. But if the system is fixed or other system, then there is some other way to calculate the value of effective length. But for now, as the system is simply supported, you just can calculate the value of effective length by using this equation or this formula. Okay, so before doing exact design, what we need is just we need the value of bending moment, that is maximum bending moment and maximum shear force. And for a simply supported case, we know that the maximum bending moment occurs at mid of the section, and we can calculate the value of that moment by using the equation, or that equation is WL effective P square divided by 8. So we have all the parameters. We have already calculated the value of all these things, and some are also provided in the equation. So we can directly calculate the maximum bending moment in the system. So we can calculate here, and we get the value 102.57 kilonewton meter. Likewise, we can calculate the maximum shear force, and this to calculate the maximum shear force, you also have another equation, that is W multiplied by L by 2. So this is actually we can like remember this formula, because uh, we cannot derive all the time this formula. So just we should remember this to get the value. If you do mistake here, then even though the process is correct, the value you get will be wrong. So be careful while calculating the value of bending moment and shear force. So here you can calculate the maximum shear force using this formula. So you can get the value of 52.3 kilonewton. Okay, after calculating the bending moment and shear force, now we have a flexural equation. So that is, okay, let me describe it here. So the flexural equation is m by I, okay, equal to sigma by y equal to e by r. Okay, where m is the moment capacity of a section, moment capacity, moment capacity. Or sometimes if you sometimes you can replace this value by the exact or the applied moment to find out the size of member. But ultimately this m is, if we use the exact size of section to calculate a moment of inertia, we can calculate the moment capacity of that section. So m is moment capacity of that section, whereas I is moment of inertia, second moment of inertia. Okay, sorry second moment of area. Okay, I, and sigma is permissible stress. Sigma is permissible stress of that material, whereas y is the distance from neutral axis to top or bottom fibers. Okay, y is uh, distance from neutral axis, distance from neutral axis to bottom fiber of a section, bottom fiber, bottom fiber of section. Okay, and E is modulus of elasticity, modulus of elasticity, and the last one R is radius of curvature. Okay, radius of curvature. I think most of you you know this equation, and yeah, I think you you can derive this equation as well. You can take a reference from strength of material, and you can easily understand, and you can derive this equation using that theory. So this is radius of curvature. Okay. So let's just just try to elaborate those like those parameter here. What does this means? Okay, so this is, for example, before applying load, this is the beam, and this is the applied load. Okay, after applying load, the beam will bend like this. Okay, like this. So if we take a section this here, this here, then then it if we extend this line here, it will meet here, and this is the center of the curvature, and this is r, which is radius of curvature. Okay, just we apply this equation, and we are just going to find out the section size, required section size of the material of that load. Okay, so look at here. So we can use this equation, and for a rectangular section, the value of second moment of area, that is I, which is equal to BDK by 12, and Y is the, as I said earlier, the distance from neutral axis to the bottom fiber of the section, so which is d by 2, as d is the whole depth of the section. So we can also like rearrange this term here. We can find out the value of m. M is sigma by z, where z is section modulus, and the value of z can be determined by I by y, where I is just the second moment of area, and y is the distance from neutral axis to the bottom fiber. And if we replace this value by these values, b taken by 12 and y equal to b d by 2, you can find out the value of z, that is section modulus for rectangular section, and that is bd square by 6 for rectangular section, and this value is different for different type of sections. For example, it is different for circular T section, I section. Okay, you can calculate that one too, but for most of the time, the section of the timber used in a real field is rectangular or sometimes square, so just you can utilize this formula. So here m equal to sigma b by z. B means like a bending. Okay, uh, so in beam, actually the beam is designed in flexure only. It is true that in beam there is very less chance to have axial load, so it is designed as flexure member. Okay, in flexure, so you can use this flexure equation directly here. So we here we have to find out the value of b and d, that is size of the section. So we can just apply here the value of m, that is 102.67 multiplied by 10 power 6 to convert Newton meter to Newton mm, and sigma b is Newton per mm square, which is 16, and we don't know the value of b and d, which is going to be find out soon. So here bd square is this much. So at this time we can assume the ratio of b and d, because both of them are unknown for us, so just we have to make an assumption of this ratio here. Okay, look at here. We can assume d ratio of the d and b is 2, that is d equal to 2b. In this way you can calculate the value of b, which is 268 mm. So you already assume that the ratio of the b and d is 2, so just double this value, and which is approximately equal to 600 mm. So we can assume 300 by 600 mm, and okay, just a slightly more value, then calculate it, and in a whole in a round up value. Okay, that is a multiple of 25, or you can also use the multiple of 50. Okay, so just we have assumed the value of b and d 300 mm and 600 mm. So now we have to check for shear, vertical shear stress and horizontal shear stress. So we have already calculated the value of maximum shear force, which is occurred at support position, okay, near the support. So V equal to B by D, and we know the value of shear force induced there, that is 53 for 52.3 kilonewton, and convert this to Newton by multiplying 1000, and just we assume the value of B and D here, so we can calculate the vertical shear stress, which is 0.24 Newton per mm square. And in a chamber, in the wooden member, there is actually the value of horizontal shear is 1.5 times the value of vertical stress. So just multiply that value of vertical shear stress by 1.5 to get the horizontal shear stress, and this is 0.435 mm square, which is safe because the permissible in the question already we have the value of permissible stress in shear, which is 1.3 newton per mm square. So this is safe in both vertical and horizontal shear. And last one, after checking for shear, we also need to check the section size is like okay, either it is okay for deflection or not. So check so the next step is check for deflection. So we have for radial load and simply supported condition, the value of deflection can be calculated using this equation, that is 5 WL for 4 whole divided by 384 EI. Actually, this is very common equation. We have been using this equation in our subjects like theory of structures and strength of materials. Yeah, in previous in while we yeah, while pursuing a bachelor degree. So we have all these values. Okay, wait. Okay, let me describe this. The what does this value means? W is the applied load. L is effective length of the section member. E is modulus of elasticity, whereas I is a second moment of area. Okay, just convert all this into Newton per mm square, as I said earlier. We are going to use Newton or mm in almost all of these questions. So yeah, we just need to convert them into Newton or mm. Newton for force, mm for length. Okay, in this unit. So just put all the values and just you can calculate the delta calculated, that is 3 This is elastic deflection, and this equation is for elastic linear elastic. So we can calculate the value of deflection at the mid of the member. So that is 3 So what is the permissible? Okay, we have just calculated the value of exact deflection in of the member while we applied load. So what is permissible value? So the delta permissible is L effective divided by 240. This equation is provided in several courses like English standards and American or development maybe. Yeah, so you can use this equation here to find out the value of permissible deflection. So we can get the value of permissible deflection is 21.79 mm, which is no greater than delta calculated, which is 3 mm. So we can show that like induced deflection is within permissible deflection, and the section size is safe for uh, that provided load. So we can adopt the size of 300 by 600 mm to sustain that load. Okay, because it is safe in moment cap, safe in moment, safe in shear, and safe in deflection. So we can add up that section size. So actually this is the wrong here. Okay, just do not ignore it here. The value of second moment of area can for rectangular section is b d by 12 for rectangular section, whereas pi d power 4 divided by 62 is for circular section, not a square section. So this is the mistake here. Just remove it here. Okay, I think Okay, this is not for square column, actually this is for circular section. Okay, no column, yeah, it may be circular column beam, it doesn't matter, just for section, the shape of section, we can calculate the value of second moment of area of that section. Okay, in this way you can design the or analyze the uh, required size of beam section. So let me summarize this at last on. So okay, so first we have just you have to calculate the effective length at first by using this equation. Look at this figure. After calculating effective length, you can calculate maximum bending moment for that support condition. So as the support condition is simply supported, we can use these formulas to calculate maximum bending moment and shear force. So after calculating these induced forces, we can use flexure equation to find out the size of the section at first, and uh, we will check these size for other forces, that is shear force, and after doing all these things, we just check this provided section for deflection, whether it is safe or within the limit of permissible deflection or not. If it is not safe in deflection, then you need to change or increase the size of section, although it might be safe in bending shear force, but as it is not safe in deflection, you should increase the depth or breadth to to make the deflection limit as given in course. Okay, for this case we are just using L50 divided by 240 as delta permissible.